Okay, so in this video, we're going to take our solids of revolution and now we're going to find the surface area of the solid of revolution. Now, in some ways, the surface area problems are a little bit easier to set up because you don't really have two different methods. The only real difference is in how you select your radius. This radius part out here in front is going to be the thing that you have to sort of worry about in terms of whether you're rotating around X or around the Y axis. Now, I'm not in this video going to do rotating around lines, Y equals 1 or X equals 3 or something like that, because it's actually much easier to figure out if you can do the shell or the washer, particularly the shell method. You just have to think about how that distance is calculated, how that radius changes, and it's really quite straightforward. The most complicated thing about the surface area problems is actually going to be if you have sort of a more complicated function than x plus 3, then the square root bit is going to be the hard part to integrate. With a constant like this, it's going to be quite easy because you're going to get a constant under the square root. But we're going to look at both what happens when we rotate around the x-axis, set that up, and then also how that changes if you rotate around the y-axis, given that we have a function of x. And of course, everything switches if you have a function in terms of y, the y variable, then everything that was true about x will change to y. You can just replace everything in your function r of y and f of y squared dy, but then everything I say about the x-axis in terms of x is true of the y-axis in terms of y, and so forth. So let's look at our example. So this is that same region. We found the volume of revolution rotated around x. Now we want to find the surface area of that volume of revolution. This is our general formula. We have this arc length component because it's the surface area. And then we have to care about the radius relative to where we're rotating it. Now, again, it's always a good idea to draw on your picture just to remind yourself how you are orienting things, so that when you're setting things up, you have that visual reminder and you don't get turned around. Now, the function in this case, y equals 1 is not a function in this context. The derivative is 0. So that's not what that's referring to. They're referring in this case to 3x plus 1. We're not worrying about what's going on in the inner part of this. We're only worrying about basically the outer portion of this. Now, 3x plus 1 is our function. So we're going to have to first find the derivative. F prime of x is equal to 3. That was super easy. And then, so that's going to go into our square root. And again, if there was an x here, that's when things get really hairy when we try and do the antiderivative. But the thing that we have to choose for our surface area is the radius. And the radius is going to be determined by, that is not how that should have pasted. Let's try this again. There we go. The radius is what we have to figure out. So let's place 3 in here. So let's think about our radius. So we're rotating it around the x-axis. The radius is essentially the distance as we do this rotation. So again, we're rotating it this way. What is the radius here of our cylinder? You can think about this as the arc length. This is the radius. This is the radius. It's essentially the distance to the axis of rotation. And that axis of rotation in this case is going to be the x-axis. And if that's the case, then this function here is going to become essentially y, the distance in y, which in our case is 3x plus 1. And then we just have to simplify. We get 2 pi. Our limits of integration, since we're in x, are going to be from 0 to 2. This square root, so 3 squared is 9 plus 1, you get the square root of 10. Which we can pull outside the integral. And we're basically just integrating 3x plus 1. So 2, I guess we could put pi first, then the square root of 10, even though that seems odd. And then when we integrate 3x squared, or 3x plus 1, we're going to get 3/2 x squared plus x from 0 to 2, which is going to give us this crazy number times, let's see, when we put in a 2, that becomes a 4. Divided by 2 is 2, we have 6 plus 2, and everything else is 0. So we end up with basically 16 pi square root of 10. You're almost always going to end up with some crazy square root. Sometimes 3/2 powers and strange stuff. So don't expect nice numbers to come out of these unless the numbers are chosen very artificially. Okay, so that's our surface area. Now, that's if we're rotating around the x-axis. Now, what if we're rotating around the y-axis? So in this case, again, we're going to rotate. I'm just going to draw it on here to remind ourselves what's going on. So we're rotating it in this direction. Now, almost all of the stuff that we started with in the previous problem are going to be the same. That's all still true. F prime of x is still 3. More. That's still 3. That's the inner radius. If I'm thinking about that volume of revolution, that surface area. But then the radius that I'm worried about is going to be the radius in this direction. That's my radius. And this is actually going to be true, regardless of which function that I'm looking at. But just look at this inner one for a second. So if I wanted to think about just this, taking this solid revolution, rotating around, what's this inner surface area going to look like? Well, that radius is just the distance. Where is that thing being rotated? It's the distance of x. Because I'm rotating around the y-axis. It's just, here's my cylinder. I'm thinking about rotating around. What is that radius? It's just the distance of x. Now, that's the only thing that differs between rotating around the x-axis and rotating around the y-axis. And then we could go ahead and simplify this. This is still square root of 10. To pi, we're still integrating from 0 to 2. Square root of 10, but I'm just integrating x. That's all that's left. And so I get 1/2 x squared. That is not, that's what I want. 0, 2, and I end up with this crazy thing. Times, this is 4 divided by 2 is 2. I end up with 4 pi squared of 10. Now that I should again keep in mind, this is this side. I'm rotating around the y-axis. Now, if I wanted this outer one, this is just a straight line. So if I wanted this outer one, I don't even have to do calculus. All I have to worry about is actually just doing the cylinder with a radius of 2, because it's 2 everywhere. So I don't even need the calculus for that. That's a constant radius. And I don't need to even worry about the f prime, because the function in this case is just, again, it depends. Again, you think about the sides that you're rotating around. This one is the one that you would geometrically have to concern yourself with in terms of the calculus. If you were doing this, this would be the inner surface area, basically. If we just jump back to the previous question, the same thing can apply in this problem. If I really want to rotate this around the x-axis and I want both the outer surface area and the inner surface area, that's easy. The inner surface area is just that cylinder, because it's just a constant here. It's a straight line. So if you think about what is the surface area of a cylinder, again, just the sides of it, you can use a geometry formula to obtain this value. It's the calculus that you need is to obtain the surface area of this portion. That again, if you're thinking about this surface area, that's just going to turn into a circle. You don't need to, you can just use geometry for that. The calculus portion that you need is for this line, this curvy part. If this part was curvy, then we would have another thing to worry about. But this is really just a straight line. The surface area of this hole that we have in the middle of our region would just be a solid cylinder, basically, the inside of it instead of the outside of it. And you could just use geometry to calculate it. What we need the calculus for is this straight line. And so the same is true for this second version of it. I'm not thinking of this line because I don't need calculus for this line. If I rotate this around the y-axis, I just get a solid cylinder. I don't need extra fancy stuff for that. What I need is the extra fancy stuff for this portion. And so if I rotate that around the y-axis, the part that I'm getting the value for the surface area for is this line, and that's what needs this formula. So again, if you're really thinking about it in terms of pieces and the sides of your solid shape, then you have several components that you have to calculate in order to come up with the total surface area. If you have no holes in the graph when you do the rotation, then there's a lot less to worry about because you have only the outer surface to worry about if it's really solid. In this case, we have an outer surface, which we can do geometrically in this orientation, rotating in this direction. And it's only the inner surface that we need to worry about in terms of the surface area formula. So you have to think about the way the problem is set up, and particularly sometimes the way they phrase these questions, they don't necessarily want you to come up with the areas of the whole. They only want the surface area that actually needs the calculus. But again, the main difference here is you don't have to change formulas depending on what axis you're rotating around. You don't have to change variables ever. You use whatever variable is given to you, and then the only thing that changes is how you define this radius. Is it oriented from the x-axis? Then it's a function. It's essentially the function itself, or the difference of the functions depending on how this rotation is defined, or it's just x because you're rotating around the y-axis. It's just the variable. If you're rotating around other lines, then you have to worry about the axis of rotation. It might be the axis of rotation minus x, or it might be the x minus the axis of rotation. Again, depending on the order and the orientation. But that's the only thing that changes.